Continuing the respiratory system. We just went through the nasal passage. We talked about the pharynx because it's shared with the digestive system. There is the uvula that snaps up to block block food from getting up into this air passage. And there's the epiglottis that keeps food from going into your trachea, your windpipe. Well, actually, your voice box right there, that's your larynx. But it's the entrance to your windpipe. And now we're going to talk about those below the throat, below the pharynx structures. You literally have vibrating strings of tissue across the opening of your voice box that are controllable by muscles. You can tighten them up and make your voice go up higher, and you can loosen them up, and then your voice is coming out at fairly a normal tone, or you can relax them a little bit more and make your voice go deeper. And of course, when you're going through puberty as a boy, the growth that's happening very quickly in your larynx can have an effect on how controllable those are, and your voice will go up and down somewhat uncontrollably sometimes, especially if you get tense. An awful lot of our vocal control comes through our mouth as well. Below this is your trachea. And then your bronchi and your bronchioles, as they get smaller and smaller, these are all breathing tubes. And it's got rings, cartilage rings. Question on the lab. And the comparison I make is to a vacuum cleaner hose. And these are doing the same thing a vacuum cleaner hose does, because we do the same thing a vacuum cleaner does. We suck air in. And if you suck air in through a soft tube, and for one reason or another, the air isn't coming in at the other end, like a vacuum cleaner, you get the nozzle up too close to a wall, or you suck in something that blocks it. Well, what you don't want to have the vacuum cleaner do is suck the tube shut. You don't want your tube to get sucked shut by suction of breathing in. At least with a vacuum cleaner, you could turn the thing off, and then if you had a soft tube, you could take whatever's off the end of the nozzle off, and then it would open up. But they'd rather you didn't need to do that. Just get off whatever's on the nozzle. In us, if you suck that tube shut, just relaxing wouldn't necessarily open it. So we need it reinforced. Is that there's reinforcements on the trachea, there's reinforcements on the bronchi. When the bronchioles get really small, there's smooth muscle, which helps to regulate the airflow, slow the airflow down when necessary, but it also helps keep the tubes open when they're a little bit too small for cartilage rings to work terribly well. But that's the main purpose of the rings, is to hold it open. It doesn't matter if you're breathing out, is it pushing out against the outside of the tube isn't gonna do anything to it. It's when you're breathing in that the issue is. Now this part of the system, the tubes are lined with, they produce mucus, and there's mucus along the whole lining. And there's cilia on the lining that's always moving the mucus up to your throat. And whether you're conscious of it or not, you're always swallowing, and that's part of why you're always swallowing. People go, oh, it's saliva, it is a little bit. But it's mostly mucus, because you need the system to be continually replenished. You breathe in. There's particles in the air. You don't want them accumulating down on the bubbles of your alveoli. Alveoli, both proper pronunciations of that. So you want to sort out all the particles as they go down. And mucus is sticky, and the air is turbulent. So odds are the particles are going to hit the mucus and stick to it. The bigger the particles, the quicker they hit something, because they have more momentum, so they're more likely, while they're stirred up, to whack against the mucus and stick there. Also, as the air gets close to the edge, there's a limit to how solid the air can hit it. You tend to get what's called laminar flow, where the air right against the mucus tends to be going this way, and little tiny particles tend to get deflected away from the sticky mucus. And they'll get down to the bottom, but they're really tiny. And they're so tiny that in your alveoli, you have a white blood cell patrol that gobbles up the little particles and carries them away. So we're pretty good at cleaning out the particles, unless we overload the system. Partially, that's what smokers do. There's so many particles in cigarette smoke that it just coats the mucus. And then when a particle comes, instead of hitting the mucus and sticking, it hits another particle and bounces back off and winds up going deeper down. On top of that, I mentioned this a long time ago when we talked about cilia. Nicotine makes cilia stop moving temporarily, but that means your clean out system, if you're a heavy smoker, you smoke a lot, is that you're paralyzing essentially your clean out system. And so it's much more coated with particles than it should be because you're not getting it out and replacing it with fresh mucus. So way more particles get down. And also tar, which is not quite particulate, but it's black and sticky and can coat the alveoli. Same thing happens in coal dust. There's a type of tar that causes black lung. It gets accumulates and really screws up with the passage of oxygen and carbon dioxide across the surface. If you have cystic fibrosis, you have trouble adjusting the wateriness of your mucus. Your mucus is too thick. It's I'm not going to explain it. But that means it's harder to move. It tends to jam up a little bit more, especially in the smaller tubes. It can make breathing really, really difficult. It can also messes with the mucus in your digestive system too. So cystic fibrosis is both a breathing issue and a digestive issue, and is really, over time, can really compromise your system. As most people with untreated cystic fibrosis are not going to last past their 20s. But it is treatable. Is that there are drugs that you can take, and there's nebulizers you can do to kind of soften the mucus up. Is that one of the problems you wind up with is cystic fibrosis being genetic, shows up really early. The kids are being treated through their whole young lives, and when they get to be older teenagers and feel more in control of their lives, they've never really, if they've been doing what they're supposed to be doing, they've never really had an issue with it. And they, at some point, go, why the hell am I doing this? Why the hell am I doing this every single day? I'm fine. And one of the biggest killers of cystic fibrosis is a teenager, young adult deciding, I don't need the treatments anymore, and clogging their systems up and dying from it. I mentioned as you get down further that there's smooth muscle in the linings that controls the flow. There's smooth muscle in the upper linings too. It can't close the tubes up in the upper linings, but it can squeeze it. That's why the cartilage doesn't go all the way around. It's like C shapes that help to hold the surface, but it is actually expandable and contractible a little bit. And again, to slow the air down, you do that. When you get down to where there's no cartilage though, anything that can really tighten up the smooth muscle can close the tubes. And that's asthma. Inflammation can cause the contraction of the smooth muscles, close the tubes, and then you can't get air through them. You can't breathe out, you can't breathe in. When they're partially closed, you're wheezing because the air's really, having a hard time fitting through. It's an allergic reaction response, sometimes a stress response, but that's what's happening. And for reasons I don't think anybody completely understands, much worse now than it was in my childhood. Kids had asthma. You virtually never heard of anybody dying from an asthma attack. Asthma attacks were considered, super, super serious. It's a much more potentially serious disease now. Not sure why. There are some theories, but not sure why. While we're talking about cleanup, So particles range from large particles that could get in there down to tiny particles. Large particles hit the mucus and get stuck there and get cleaned out. Tiny particles, and this is not to scale, this should be smaller down here, are eaten by your white blood cells. There is a range in between that is not effectively caught on the mucus and is too big for your white blood cells, which you can't effectively clean out of the air coming in. To which you go, well, that seems really weird. It turns out there are almost no natural particles in that little bit of range. So in the natural world, we don't run into those. So our ancestors didn't need a system that didn't have that gap in it. They didn't need to close the gap. We do now, because we do have particles that are produced artificially that are in that gap. One of them is asbestos. Asbestos is a fireproofing agent. It's in buildings like this. They used to put it in the walls of the building because it's inert. And fires wouldn't burn past the walls because they'd hit the asbestos and couldn't burn through. So a lot of old buildings had asbestos, and it took a very, very long time for somebody to realize that the asbestos could evaporate very slowly. But the evaporation potentially put particles in this size into the air. And they already knew that if you worked in an asbestos factory, you would accumulate these particles. So they knew that there was a potential problem with asbestos because mesothelioma and lung cancer and other sorts of things are associated with asbestos inhalation, either in mines where it's mined or in factories where it's processed. Nobody expected it to come into the air in a building where it was in the walls. So they went a little nuts. And so now there's all sorts of regulations mitigating asbestos removal, where if you're tearing it out, you definitely got to worry about the particles. But also, people have kind of freaked out about it. It turns out that the asbestos particles that do actually evaporate tend to actually be in this range. They are actually catchable by your white blood cells. So probably in a building where nothing has been disturbed, even though there's asbestos in the air that's readable as a small level of asbestos in the air, exposure to it is probably not accumulating it in people's lungs. Not going to change the regulations, but because it took like 30 years to figure that out. Where are we? Oh, not too bad. Okay, get ready to write because I'm going to show this rather than write it down. Breathing. Your chest cavity is a sealed system. If you expand the volume of this sealed system and there's access to air, then these lungs will inflate to fill up that extra space. That's basically what happens when you inhale. You increase the space in your chest cavity and your lungs expand to fill that extra space. You squeeze the chest cavity closed. The easiest way to get rid of the excess volume is for the air to go out. It's that simple. But there's two major drivers of breathing in, inhalation. And that is this curved diaphragm, which you saw in the pigs, right? It was this big dome muscle. That goes down, and of course, it goes from up here to down there. It expands the space in the chest cavity, and the lungs inflate to fill in that excess space. The other thing that happens is your ribs are, they attach to your backbone, but they attach at joints, at movable joints. And you can actually, with the muscles in your ribs and other muscles, you can actually swing your rib cage, up slightly, and swing it up. If you breathe, you can feel a little of that if you have your hand on the bottom of your sternum especially, you can feel that swing up. It doesn't change the volume a lot, but it is part of what makes inhalation work. I've seen people argue about, the best way to breathe if you're an athlete or a singer or, controlling your diaphragm and all sorts of things. But those two things do work together. And then the one thing you got to worry about is if air can get out of your lungs into the space, into the liquid-filled space of your thorax, your chest, then, so there's a hole, and the air goes out, and you start to breathe out, and the hole, because the lungs are closing, closes up. So the air goes out into the space, but can't get back out into your lungs. And a punctured lung can gradually fill your chest cavity with air and deflate your lungs because there's no room. You know, your lungs try to inflate when you try to breathe in, and eventually you can't breathe in because you can't expand, the air's trapped. You can't expand the volume of the chest anymore. And there are some diseases that compromise the lining of your lungs and can do that. A puncture wound, bullet into the lungs, a knife into the lungs. You see in the medical shows where they'll poke a hole between the two of the ribs and shove like a pen casing or, you know, a straw in, and you could see the air come out, and a little bit of fluid, in order to get the lungs to reinflate. One more thing. So your blood is carrying all sorts of materials. Some of those materials evaporate really easily at body temperature. That's part of what makes them go out into your lungs and get breathed out. Carbon dioxide evaporates out of your hot plasma really, really easily. It's dissolved in the plasma, but it moves out into the air and is gone pretty easily. It turns out other things do that as well. Ethyl alcohol does that. If you have ethyl alcohol in your blood, when you are breathing out, there's a certain amount of ethyl alcohol that's evaporated out of your lungs and is coming out. It's not in the linings of your mouth from drinking. It's in your actual blood. And so all the stuff about, you know, all the tricky things people want to do, you know, up here to kind of fool a breathalyzer, doesn't fool a breathalyzer because it's not reading the surface of your mouth. It's reading the actual air that you're pushing into it. Other things, one of the smelling ingredients in garlic also is excreted that way. And so excretion through your lungs, anything that easily evaporates at body temperature can be, and will dissolve in your plasma, can be lost through your exhaled air. It isn't, carbon dioxide, you're literally removing a body waste product. All this other stuff is it's just kind of leaving that way. Okay, that's it for the respiratory system. We're going to move through the systems relatively quickly as we go farther in. Before we get to the nervous system, the other systems are fairly simple. They're probably all going to fit on one video. Each one's going to fit on its own individual video. So these will tend to be shorter, I hope. You know, I have to stop myself from talking. That's not easy.